Welcome to the Calculus AB video for skill number 140. I can find the derivatives of trig functions. Alright, so we've talked about the top of a capital, or the top of a column being called a capital, and I made reference to the ionic order being really common with having these scrolls at the top. The trivia question for the day is, what is this scroll called? Alright, so this skill is largely about just memorizing derivatives of trig functions. So we have our 6 trig functions, and, well, you just got to memorize them. So the derivative of sine is cosine, and the derivative of cosine is negative sine. The derivative of tangent is secant squared, and we will derive that, just so you can see why that is. And we could derive the rest of them, but derivative of cotangent is negative cosecant squared, and the last two you can see below. In truth, the sine and cosine ones are the ones that are going to pop up most frequently, so you'll need to commit those to memory, and I encourage you to memorize them really well, because it's easy to get them mixed up or backwards. Anyways, so the first example is just a straightforward find the derivative of a function. And what we have is 2x to the third minus 5 sine x. So what we can do is we can first take the derivative of 2x to the third. And the derivative of 2x to the third is 6x squared. And then we subtract from that the derivative of 5 sine x. And we remember that the derivative of sine is cosine, so the derivative of 5 sine x is 5 cosine x. Pretty straightforward derivative calculation. We're not quite to the point where we're going to start using the derivatives for anything too meaningful, but the next chapter, the next unit, we really move into applications of derivatives. So right now we're just churning through learning how to take the derivatives of all types of functions. A very basic application problem is about what you have is a weight that's on a spring, and it's kind of bouncing up and down, and the function that models it is, the position is 3 cosine t minus 7 sine t, and we're asked to find the acceleration of the spring at t equals 5 seconds. So what we can do is we pull from our last skill and know that acceleration is the second derivative of position. So we write down our position equation, find the first derivative, and that's our velocity equation. And then we find the second derivative, and that's our acceleration equation. We're interested in knowing the acceleration at time 5, so we evaluate acceleration at time 5 by plugging 5 in for the variables t. And in radian mode, that arrives at negative 7.56 meters per second squared. It's important that I stress that I said in radian mode, because these derivatives only hold true in radian mode. So we want to make sure that we're in radians when we do our calculator skills with derivatives and trig functions. Example 3 asks us to use the quotient rule to prove that the derivative of tangent x is secant squared. And the way we do that is we can rewrite tangent x as sine over cosine. And that allows us to see that what we have is a quotient of two different functions, and we can identify sine as f and cosine as g, and apply the quotient rule that we learned 2 skills ago. And filling that out, we wind up getting f prime g minus g prime f all over g squared, and we see that the numerator is a Pythagorean identity. Quick review of the old trig: cosine squared x plus sine squared x is equal to 1. Pythagorean identity. So we can simplify our numerator to be 1, and 1 over cosine squared is secant squared. There we go. So knowing only sine and cosine and a little bit of trig, we were able to find the derivative of tangent. So if you don't remember that, maybe you can go the long way.
Can I get a smile? Congratulations. You just changed my day.
Alright, and then our standard basic calculus question where we're asked to find the equation of a tangent line, or in this case, we're asked to find the equation of the normal line. So in this case, what we have is a function that kind of is going up and down. I don't know exactly what sine x plus cosine x looks like, but at x equals pi, we are interested in finding not the tangent line, but the normal line. So the equation of the normal line, the one that's at a right angle. So if we want to do that, first we need to find the slope of the tangent, and that means calculate the derivative of the function. And so we take the derivative of the function and we plug pi into it, and we get the slope is -1. So if that's our slope of our tangent line, then our normal line is the opposite reciprocal of that value, so 1 over -1 negated, and that gives us a perpendicular slope of 1. And so we want to create an equation that has a slope of 1 and passes through pi f of pi. And if we stick pi into the original equation, we get y equals sine of pi plus cosine pi, and that is y is equal to -1. So f of pi is -1. Stick that information into our point slope equation, the go-to for all line equations, and we find that y plus 1 equals 1 times x minus pi is our normal line equation. And I graphed both equations on a graphing calculator and witnessed that I had done this correctly, because I had a curve that looked roughly like that at pi, and then I had a line that looked roughly like that. So it appeared, at least on the grapher, to be correct. A great way to check your work. Alright, thanks for watching the video. Hopefully at the end of this you're able to do derivatives of trig functions. For example, the derivative of sine x. If we take the derivative of that with respect to sine, we get cosine. Later on we'll get into what's called the chain rule, so we can take stuff like the derivative of sine 2x to the 5th. So that gets just a little more tricky, but the chain rule is actually pretty useful because it allows us to do a lot more things. The answer to the trivia question was, what is this scroll at the top of Ionic capitals called? This is called voluting, or the volute, and that's spelled V-O-L-U-T-E. Alright, V-O-L-U-T-E. Alright, thanks for watching. Have a good evening.